We're live.
It happened. It happened. It happened. It happened. It happened. It happened.
Did it? Did it? Well, wait. I require some kind of external validation that the wavefront has been collapsed. Then I will. Then I'll believe it happened. There we go. We're live. I want to talk about.
That's not the "it happened" I meant.
I want to talk about Artemis, but we should wait. So, all the things I want to say, we might as well just talk about it in the show. So, never mind. I'm just gonna hold my tongue.
Very exciting, though.
The launch that shall not be mentioned.
What?
Yet.
Yeah, we'll mention it shortly. Apart from that, nothing. So as I was mentioning to the folks here, there's a really cool picture of Titan on making the rounds on Twitter. If you want to go and check that out. And Space Geck, Judy Schmidt, has tracked down an image of Saturn. So yeah, this isn't a story. So Miri, as we all know, Miri had gone offline because one of its grading wheels was experiencing excess friction, and so they pulled that mode offline on Miri until they could sort out the problem, and then they came back with the answer, which is use it very carefully in very specific ways, and they can sort of make the friction happen very low. And this is important because Saturn, they get the last chance to see Saturn's northern pole before it sort of switches seasons. It's going to go behind the sun. It's going to switch the seasons, and we can no longer see the top part of Saturn for 20 years. So this is JWST's last shot, and so it's really good.
Maybe by then we'll have JWST's successor launched.
Well, but apparently, I think I mentioned this before, but the orbit placement from ESA was so good that they've got at least 25 years of life for JWST at this point.
At some wavelengths. Because they're going to run out of coolant at some point on some of the deeper wavelengths, I think. There's only 5 or 10 years of coolant, I think, for some instruments.
On just the one instrument.
Yeah, but in warm mode, and what would have been Spitzer warm mode, it can go on a long time.
But even just default mode, because of the sun shield, it's able to stay pretty cool that way. And then the other thing that was really cool that they talked about this week is they have a plan for the micrometeorites. So they're going to be, they had 12 micrometeorite impacts so far, including the big one. And the plan for cycle 2 is they're going to turn the telescope. They're going to plan out the entire cycle so that it's always looking back from its direction in orbit. And so then that will minimize the number of impacts that it experiences, because instead of facing into the wind, it's now going to be facing back from the wind. And by wind,
that's kind of a bummer, though, right? Because the whole point of sending James Webb out to L2 was to give it almost total freedom of where it looks. That was the big win over Hubble, where you can't look at the sun, you can't look at the Earth.
Right, you're always looking at the Earth. The Earth's always in the way.
So that's definitely a setback. Although there must be some neat science about why there's so many more meteorite impacts at the energies that they're seeing than they expected. Because there's no way they didn't foresee this.
Well, they are going to plan to just, I think, more carefully plan observations. So if they absolutely do have to look that direction, they can plan more carefully.
Yeah. It's all they can't. It's just they're going to try and make as much of the observations be when it is behind the telescope in orbit as opposed to in front of the telescope in orbit.
Makes total sense. It was just we were hoping to be free of that.
Yeah.
Look where we want to look.
Yeah.
And now look at us.
Yeah. Stupid telescope. All right. Let's get on with the show. Hello and welcome to the Weekly Space Hangout for Wednesday, November 16th, 2022. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about Artemis, of course. We're going to be talking about Ice Cube Neutrinos seeing an active galaxy. We're going to see the closest black hole to Earth. The History Channel found a piece of the Challenger and a really cool picture of a protostar from JWST. Joining me this week, we've got Carolyn Collins-Peterson. Hey, Carolyn.
Hey there, how you doing?
Good, good. We've got Dr. Morgan Renberg. Hey, Morgan.
Hey, Fraser, this is just a loaded episode. I'm so excited to be
I
here.
know, I know. I'm actually just
This is
skipping right
just-
past the intros because there's
this is
like
crazy.
I'm nervous in my mind that we're gonna have enough time to get through it. And we've got Dr. Leah Jakes. Hi, Leah. Is she there? She's muted, I think.
You're muted, Leah.
Oh no, sorry.
Yeah.
Just saying hi. Excited to be on for this episode. It's going to be a good hour.
Yeah, this is going to be a good one. All right. So before we get into this week's guest, WSHcrew.space, go there. All right, moving on. We've got a special guest, Dr. Jacob Izraelevitz. Welcome to the show.
Hello, thanks for having me.
So the question I always ask people, who are you? What do you do?
So I am in a robotics group at JPL. Mechanical engineering background, and I am running our Venus balloon development effort internally within the lab. So
Now, I mean, we've talked quite a bit about NASA's plans to go back to Venus. We've got the Da Vinci Plus, there's the Veritas. Neither of those are going to have a balloon.
No, this is purely tech development. So we're getting ready for future mission opportunities, and it's my job to get us ready.
So I guess in your perfect world, what would a balloon mission to Venus be like? What would happen?
So step one is we get to Venus, right?
Okay.
The deployment of the balloon actually happens while we're still in the atmosphere before we land. So it's drawn out of the aeroshell using the parachute, and we start inflating it with helium. So once we are fully inflated, we drop the parachute, we drop the tanks, we drop the aeroshell, and we go on our merry way. Balloons on Venus are very nice in that you can last there a very long time. So these types of balloons have actually flown on Earth for over an Earth year. It's that sort of length of a duration.
I think billionaires have flown around the whole Earth on them.
Yeah. So it's well understood technology. The materials you need to use for Venus are a little different. So, we have to make balloons out of them to, confirm that we can actually do that.
And so, like, what altitude? Like, I'm sort of envisioning, like, I know that as you get to higher and higher altitudes, the temperature and pressure on Venus become less lethal.
Yes.
What altitude regime do you think you would be flying at?
Yeah, so it's about 52 to 62 kilometers above the surface. So if you compare that to Earth, I mean, people start arguing that that's space on Earth, right? Once you get that high. On Venus, you're still in the atmosphere. And it's actually very similar atmospheric density and pressure to sea level on Earth. So we can actually fly balloons here on Earth at densities very similar to what we fly on Venus, and we can use that to measure our balloon dynamics and make sure that our models are correct for when we actually fly on Venus.
And I know, like, the atmosphere, while Venus takes a long time to turn once on its axis, the atmosphere is whipping around Venus very quickly. How quickly, or I guess how often would you be able to do a complete survey of the planet?
So we go around every 5 to 7 Earth days.
Wow.
It depends a little bit on your altitude. Yeah. So the winds from east to west on Venus, they're the zonal winds. They're extremely strong, extremely consistent. So turning around is hopeless. You'll never turn around.
Right.
Right. But
You're going hundreds of
it's a really
kilometers an hour. You're not going back.
Yeah. And the types of balloons we've been designing at JPL are actually variable altitude balloons. So as we get blown around the planet over, a multiple month-long mission, you can actually be scanning multiple altitudes as you go around.
That's amazing. So what kind of technique, engineering wise, would let you go to different altitudes on Venus?
Sure. So we're a 2-chamber balloon, and we move helium between the chambers to change our volume so we go up and down. So the inner chamber is essentially a helium tank. It's made out of Vectran, the similar material that was used for the airbags for Mars landings. And the outer balloon is Teflon coated, because one of the quirks of the Venus atmosphere is that there's all the clouds are made out of sulfuric acid aerosols.
So quirky.
So yeah, so while while the temperature and atmospheric density are very similar to Earth, the gases are quite different. And so that outer balloon is Teflon coated, and it protects our inner reservoir. So this type of balloon, we actually expend energy to go down. We're using a pump to compress the helium, stick it into that reservoir. But going up is free. You just open up a vent between the two chambers and up you go. So you can think of it sort of like a reverse probe, in that going up, you can go really quick, and going down takes time.
Right. Unless you wanted to go down one last time.
Unless you want to go down one last time, the swan song.
Right.
So,
right.
Yes.
And so what suite of instruments would you be able to carry in the atmosphere of Venus like this?
Sure. So we've got a couple different mission concepts that look into this. So this balloon that's showing here is it's about 100 kilogram gondola below the balloon, and about 20 kilograms of that or so is instruments. And so we talk about flying a mass spectrometer, but this is a fancy mass spectrometer. It's got an aerosol separator on the front end, so you can actually get spectra separately of the gas in the Venus atmosphere, but you can also concentrate the aerosol particles from the clouds and get specific spectra of those. So, while the aerosols are mostly sulfuric acid, there's all of this unique chemistry in like that last 10% or so that folks are very excited about.
And it requires concentrating from the atmosphere to get to the point that you can actually take a proper sample.
Exactly. So now, so the mass spectrometer is sort of like the big instrument. We also talk about flying magnetometers. So Venus does not have a magnetic field, but it once did. And the history of that loss of magnetic field is expected to be able to see it in the rocks on the Venus surface. This is what people call it paleomagnetism on Earth, looking at the history of the magnetic field. And so now magnetic field strength goes down as R cubed, and so the closer you get, the better. So we're expecting to get much better maps of what's called the remnant magnetism on Venus from this type of platform.
So what kinds of big scientific questions would you like to answer with a mission like this?
So the atmospheric chemistry is a big push. So it's investigating the sulfur cycle on Venus and the phosphorus cycle on Venus. Now, there's good chance that both of these are sort of driven by volcanic activity on Venus. So it's sort of like, in some extent, you're like sampling subsurface by just looking through these aerosol chemistries in the clouds. I also want to add that one of our other instruments is actually a infrasound barometer. So something sort of funny that folks don't necessarily know about is you can actually listen to earthquakes from the atmosphere. Yeah, so when the ground moves, it actually couples into waves into the atmosphere, right? And those waves end up being in the infrasound range. And so people do this on Earth. We've flown some infrasound barometers above the Ridgecrest earthquakes in California a couple of years ago, and could reconstruct where some of the aftershocks were from. And the big push is to be able to do that on Venus, though, right? So having a seismometer that survives the Venus surface is very difficult, and surviving the Venus surface for a long enough time that you actually have a high likelihood of seeing such seismic activity is hard.
That's amazing.
But a balloon can last a very long time.
Insight on Venus, but in the air, as opposed to on the surface.
Yeah.
I'd never even heard about that. That's amazing that you can actually pull that off. So I'm sort of envisioning you're going to be analyzing the geological history of Venus. You're going to be sensing how active the planet may still be inside. Obviously, sampling the gases in the atmosphere. The big question, maybe controversy, is like, was Venus ever habitable? Maybe is there some kind of biosphere in the atmosphere right now? Do you think those are some questions that you could cast some light on?
We can certainly, so the phosphorus cycle on Venus is something we're very interested in measuring. So the detection of phosphine itself, which I'm sure is what you're referring to with
Yeah.
is Venus habitable today? That's still controversial. So this would be able to shed some light on that. I'll also add that the heat balance of the planet is based off of the different solar and infrasound fluxes that it gets from the sun, but also it re-radiates out to space. And all of that is moderated by the cloud deck from all the way up to the high atmosphere now to the surface. And so being able to measure that balance in a global sense around the planet as you go around is very important.
So I don't get it. Like, Venus is close. It's relatively easy to reach. It's quick to reach. It has the acidic atmosphere that's just idiot proof to decelerate into, unlike Mars. This technology you're talking about has been used fairly successfully here on Earth for decades. Why is this not happening already? What is the giant challenge that has stopped this kind of exploration of Venus to date?
Well, I mean, we're building bigger and bigger balloons, right? So the Soviets have actually flew balloons on Venus in the 80s. Fun fact. So these were small probes dropped by, I guess you'd call them probes, dropped by the Vega landers as they descended through the atmosphere. And so a lot of the work, and actually one of the veterans from that program, Viktor Izraelevitz, came from the Soviet Union to JPL and helped found our own balloon program. So a lot of it has been trying to expand what was a small balloon demo into something that can carry a much larger set of science instruments, and also to be able to scan those instruments over a wide altitude range also helps improve the science. So that's been something that we've been pushing for a lot recently.
And I mean, I'm sure at a certain point, when you have a hammer, everything's starting to look like a nail. This kind of exploration of other places, where do you think balloons like this could also be used in the solar system?
So we've actually done some work on balloons for Titan before at JPL. These are very different materials. It's a cryo environment, right? And there's no sulfuric acid, right? So the balloon envelopes end up being made out of something different. But that's also something that we've done some work on quite a bit.
And I know there's been ideas for balloons on Mars.
Yep. Yep. Those end up being very lightweight gossamer-like materials. So think the type of balloons you would fly in the stratosphere here.
So if your tests are successful, when do you think we could see a mission going to Venus, a balloon mission to Venus?
Well, so we track different mission opportunities. If everything goes well, and we're able to actually land some of those, it might be in the 2030s, something like that. A lot of that depends on people's appetite for more Venus missions. So if this excites you, make sure to tell other people so they get excited as well.
I mean, is there a way to replace Da Vinci Plus and Veritas with this? No, that would be just mean.
That would be mean. That would be mean. No.
Yeah.
But our big success this year, which is I think why our media office reached out to you all, is we had a successful flight of one of our subscale prototypes. That's this one here in this picture, flying at atmospheric densities very similar to where you'd want to fly on Venus. So this is about a 1/3 scale prototype to the type of balloon you would expect on Venus. It's got a reservoir inside so we can exchange helium, and during this flight we were able to demonstrate that altitude control. We were able to rise and fall about a kilometer-wide band or so over this dry lake bed.
That's amazing. Well, it's really exciting. If people want to keep track of your work, what's the best place to do that?
So if you go to the JPL News website, you'll find updates there. We also have a JPL Robotics page, and so we also post some updates there as well.
Well, Jacob, absolutely fascinating. I'm super excited. I've done videos about this in the past, and I really cannot wait to see something loitering inside the atmosphere of Venus for a long period of time. It'll be a boon to science. So good luck with
Thank you.
your project. Thanks. Very cool. All right, let's move on to the big news. Morgan.
It happened.
Finally.
It happened. We've been waiting since, basically before the Weekly Space Hangout existed to be able to sit down and have this conversation. And we've been waiting 50 years for the launch of a rocket that is more powerful than the Saturn V. So, very early this morning, we saw the successful launch of Artemis I, the first of the new Artemis program missions to the moon. But maybe even more importantly, we saw finally the launch of the Space Launch System, NASA's sort of super mega rocket of the near future. And it wasn't without its challenges, just like every SLS attempt to launch over the last year or so. It had issues with leaks of its hydrogen fuel tanks. We've talked before on the show about the difficulties of working with a gas as light as helium. It leaks out of basically anything. It is obviously super flammable. So major props to the three guys that went out to the launch pad and were cranking away on bolts on the side of the launch vehicle as it was fully fueled up. That is, they slept well tonight, I think. And there was issues with the Ethernet on at Kennedy. It was stumbling blocks here or there, but the headliner is that at 1:47 a.m. Eastern time, it lifted off and made seemingly a basically flawless flight to orbit. All the engines were nominal. The various sequences ticked through one by one. It then performed a successful translunar injection burn to push it off towards the moon, and it is blasting away now towards the moon. About a little less than a day into what will be a 26-day nominal mission, and that'll take the Orion capsule on to a farther point from Earth than anything else we've ever sent that was intended one day to carry humans. And so it's tracing out what may be an orbit that we'll see happen for Artemis II, which in theory will have astronauts on board in mid-2024. This is very much sort of the Apollo 7 of the Apollo series, doing the first dry run with everything on board, test dummies and all, to show that the life support systems, the communication systems, the maneuvering systems, so on and so forth, work. This is the second flight of Orion, and so there's still a lot to shake out there. And that'll carry all the way through the end of the mission, where it will arrive back at Earth to do an aerobraking maneuver at really pretty high speed. And that'll demonstrate the sort of core integrity of the heat shield and the overall re-entry system. So I guess the last thing I'll say before we kind of open it up for gee whiz wow comments is it is taking kind of a weird orbit. And I tossed an orbit graphic into our list. It's taking what's called a distant retrograde orbit, which is not what we saw happen, say, with the Apollo missions, where it is sort of flying around the Lagrange points of the moon going around the Earth. And so it'll have these sort of strange close approaches, and then it'll wander quite a distance from the moon, and then it'll catch up to the moon again, and then it'll do one sort of gravity assist to redirect it back towards Earth about 2 weeks or 3 weeks into the mission.
Wow,
and so
I've never seen that before. That's
no,
amazing.
This is very different than our traditional way of thinking about sending something to the moon, which will allow the spacecraft and the instruments on board to explore parts of the sort of translanar environment that were not sampled during Apollo, or really even during some of the spacecraft missions that have gone there and kind of entered basically low moon orbits.
Those kicks with the moon's gravity are kind of amazing. Like the one where it gets slingshot around, and then the one right now where it just drops and falls back to the Earth. That's kind of incredible. Wow. I've never seen that. That's amazing. Carolyn, you watched the launch. What was your experience of it?
Well, I was watching on our big screen TV, and it was kind of like I was 16 years old again watching a launch. And I have to say, I had a group of people that I know that were out there filming the whole thing in 8K resolution. They set up cameras like 2 weeks in advance, so that you could watch it live in real time in VR if you wanted to. And I didn't think of it until the last minute, but instead I just watched it on my big screen TV. But yeah, a couple of things I noticed. One of them was, boy, those solids really light up fast. I'd forgotten how fast they go, and how messy their clouds are when you compare it to the shuttle engines that were, the main stack engines, how we're burning so clean you can almost see up into the bell of the.
And Carolyn, I was surprised, kind of pinging off that, how fast it lifted off. Like the space shuttle would light, and it would almost space shuttle would almost hover there for seemingly longer than it should every time, and this just leapt right off at a speed I was not prepared for.
Yeah, people that I know that were there were talking about how fast it went, and the noise. I mean, I've been to several of the launches, and the noise, if you even at press site, it's just rattling your body. I can imagine what this felt like. And I've heard some of the recordings online, but they just don't, they don't touch what it's like to be there.
Leah.
Yeah, I unfortunately didn't stay up to watch it, but I woke up to see all of the good news, so I didn't have to be stressed at 1 o'clock in the morning. And yeah, definitely super exciting to see this, and hopefully they get some good science out of it, getting to see, study more of the moon. Yeah, super exciting.
I mean, we did a live stream of it on the CosmoQuest channel last night, and Pamela is engineering right now, and she's mentioned this as well. There was no sound on the NASA broadcast. It was silent, and that sucked. And the camera positions were terrible. There was, like, the launch looked cool, and then it started to take off, and then they switched over to graphics of it. And we've just gotten so spoiled from SpaceX showing us cameras on the boost.
That's what everybody was saying. Yeah.
And
I'm hoping that some of those cameras are there and they're just not rigged for live transmission, and that we'll see in the aftermath, after it arrives and they come and download the data, that we're going to get some better views. Because you think it must have been instrumented out the wazoo for this first flight.
Well, since it's a test flight,
be there. Right, it's got to be there somewhere.
Yeah.
So, Morgan, describe your ambivalence. You've got to be feeling ambivalent right now about this whole project.
I mean, it's hard. Yeah, we've been doing. How long have we been talking about this?
I don't know.
Forever,
since the dawn of time.
Months,
for a long time.
Yeah,
and I think there's relief, maybe more than anything, maybe even more than excitement. I think it's hard to sort of reckon with how big the last 12 months have been for sort of like the future of NASA. Basically since like 2005, there have been, these dual programs hanging over the head of NASA, being James Webb and the various things that have become SLS, Constellation, to yada, 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 yada. Mm-hmm. Either of those programs sort of failing would have been like a disaster that we sort of can't fathom for NASA. A Hubble not seeing level of disaster that, would threaten sort of the foundation of NASA's viability going forward. And it felt like we had these sort of swords of Damocles hanging over our head for years and years and years. They were stealing money from other programs to keep them going. There was seemingly a never-ending list of little technical problems. And now, finally, they're both done. Mm-hmm. And seemingly all that time and all that energy and all that money poured into them was for success, because they both, did the thing on the first try. And will it be a long-term success? I think that's cloudier than ever with the way we're seeing Starship and other heavy lift rockets go, I mean, just yesterday, NASA gave SpaceX a new contract for more landings on the moon.
Yep.
It's clear that they're continuing to move forward with commercial spaceflight. But had SLS not worked, had Orion not successfully worked, it would have been a disaster.
Yeah.
And so to get through that, regardless of where we go now, is going to open the floodgates of opportunity for things like a balloon on Venus, where that money was being whisked away to feed the black holes that were SLS and James Webb. And now they're alive and in the world, and we can enjoy them, use them, but think about other things.
It does feel like a beautiful success of a dead end.
Right. This is the pinnacle of the old spaceflight model, right? They spent an unfathomable amount of money to make the thing work on the first try. And there we go. It worked almost flawlessly on the first try. But in the meantime, all of these other ways of doing it have caught up in one respect or another with that old approach. And where do we go with this approach now? Why would you spend, $10 billion to make it work on the first try when you could spend $1 billion to have it work on the fifth try?
Right. Or spend $1 million and have it go on Starship. Yeah, like that's going to happen. But anyway, with Gwen Shotwell's company, SpaceX. All right. Well, it was exciting. So what's the next big event that people should be paying attention to?
Yeah, so it'd take about 5 days for it to arrive for its first close approach to the moon. There'll be a couple of burns in the interim to do, some course corrections if necessary. And then it'll start making its first approach, and we should get some great pictures of the moon as part of that. And then it'll kind of go through that weird sequence that we were looking at of close and then far and then close and then far before it makes its gravity assist back to Earth, which will be sort of early December. And then presuming everything goes well, the next launch, Artemis II, is slated tentatively for May of 2024. And in some ways, if they can pull that off, like that's feasible, right? That's within this term for President Biden. And so the political will won't really change between now and then if this mission goes well. And that should be a crewed mission that carries out a similar mission for a couple weeks to fly by and past the moon and basically return astronauts beyond low Earth orbit for the first time. And I think watching this today, that's the thing, is for the first time, maybe I actually believe that this is going to happen. If Orion works, if SLS works, there's really not a lot on a technical side to keep it from more or less staying on track. And politically, the money will be spent, whether Biden gets reelected or doesn't run or whatever. The money will be spent before his term is up to make the next mission happen.
I mean, the big unknown at this point is the SpaceX Starship lander. Everything else is dialed in. The core stages are under construction. The upper stages are under construction. The Orion capsules have been ordered. Like everything is
right. So Artemis
in
3,
production,
which is supposed to be the first landing, including the SpaceX lander, is scheduled for 2025. I would not bet very much money on that. Yeah. But the idea that we could get astronauts out of low Earth orbit in 2024 suddenly seems like a doable thing. Mm-hmm. And that I would not, a year ago, I would not have put a lot of confidence into that.
Yeah, that's almost like tomorrow.
It is, basically.
And having humans fly farther from the Earth than it's ever been done before is exciting. I think
yes.
It's a good next step.
This is the first time I feel excitement about this in a long time. It's not, elation, but it's not mediocrity.
Yeah. We had reported on Universe Today that NASA has ordered the Orion capsules for, I'm going to say 6, 7, and 8. Like that's how far into the future this
Those are 2030s. Those are 2030s.
Yeah, ending by 2030 is the last one. So that's how far into the future they're already starting to plan out these missions. So obviously, if something really incredible comes out of SpaceX, then things may change. But apart from that, you're going to see more of these gigantic rockets lift off. Very cool.
I want to go see one in person.
Yeah, me too. Me too. All right, Leah, let's talk about neutrinos coming from an active galactic nuclei.
Yes, this is a super cool story. So we just had things leaving the Earth. Now we have neutrinos coming to the Earth. So basically, this was a couple weeks ago. There was a press conference from the IceCube Observatory Experiment. An IceCube, basically, for those who maybe don't know, is a observatory at the South Pole in Antarctica. It's buried under, I think, 1 billion tons of ice. And there are detectors that go down 2 kilometers into the ice looking for neutrinos. And they're looking for neutrinos, also looking for some dark matter signatures and things like that. And a couple of weeks ago, they had this press conference and they shared that they detected 79 very high energy neutrinos from the active galaxy NGC 1068, which is also Messier 77, if you prefer that naming scheme. And this is exciting because to date, we've only seen neutrinos from the sun, from the atmosphere, and from one other active galaxy that was a little bit different than this one. And this is exciting because when you have an active galaxy, there's a supermassive black hole at the center that is powering these very energetic jets at the center of the galaxy. And there's a lot of gas and dust that kind of obscures what is happening in these galactic cores. And by observing these neutrinos, it gives us a window into the astrophysics that's happening in these cores. So it's an exciting kind of opening up a new window of ways that we can learn about active galaxies and their particle content and neutrinos that come from them.
So do we have a sense how different supermassive black hole neutrinos are from sun neutrinos?
So my understanding is that these are much, much more energetic. So the ones that they were detecting in this announcement, I think were on the order of like a tera electron volt. And I can't remember off the top of my head what the average for a solar neutrino is, but I think that these are much higher energy. And so that's how they can differentiate them.
And when you think about how many neutrinos you have streaming through your body at all times, and they just pass through your body, like there's got to be these fire hoses of neutrinos coming through the Earth from all these different directions. It's just a matter of being able to dial them down to go, yes, these are all coming from this one galaxy.
Yeah, exactly.
Now, this is still like the standard? They haven't upgraded IceCube yet to the bigger version yet, have they?
I don't believe so. I think
No.
this is the standard kind of version.
Yeah, the cubic kilometer, because they're gonna be shifting to a 10 cubic kilometer version next. But
yeah, they definitely have not done that upgrade yet.
Yeah, Nancy is saying that we've got the principal investigator for IceCube coming in December, so I'll save all those questions for them. So then, I mean, I guess one of the sort of exciting things is we're starting to really enter this realm of multi-messenger astronomy. You've got gravitational waves, you've got electromagnetic radiation, and then you've got neutrinos. So we can obviously see M77, and now we can detect the neutrinos coming from it. So what kinds of like compare and contrast, how would you want to be able to blend those two data streams together to give you some answers about the galaxy or about black holes or accretion disks or anything?
Yeah, so I think, well, one of the like exciting things about this is that generally we can't see anything into these types of galaxies, into their the supermassive black hole, the jets. Like there's too much gas and dust that's obscuring our view to learn about like the dynamics in these systems. And so I think that detecting anything at all is amazing. We learn something from there. I was also reading that potentially with JWST for these types of sources, because it's looking in the infrared, we'll be able to see more than we might just looking in the optical. So if we had some sort of coincident JWST observation with a neutrino observation, I think that would be able to tell us, maybe some information about how these accretion disks form, the masses of the black holes, the kind of dynamics of the jets, things like that, which I think are all important questions.
One cool thing about neutrinos is that sometimes they are the fastest messenger. And that's strange because we think of light as always being the fastest. But light gets intercepted and redirected by all these things. Neutrinos get intercepted and redirected by basically nothing. Mm-hmm. And so, in the sun, for example, solar neutrinos leave the sun like milliseconds after creation. Rays of light, photons from the center of the sun, take tens of thousands of years, maybe hundreds of thousands of years to make it to the surface. And so when you can detect differences between the arrival time of photons and the arrival time of neutrinos from an event, that gives you a window into the physics that was happening around there, because the neutrinos are going to tell you when the thing happened, and the light is going to tell you when other conditions allowed light to be emitted and escaped from that area.
Yeah, there's a neutrino warning network that's working right now, waiting to hear from a supernova, and they'll detect the neutrinos, and then they'll know to go looking for the supernova. But it has to be within like a few hundred light years of Earth to be effective. But yeah, you get the situation. The supernova goes off, the neutrinos escape immediately, the photons pile up inside the star, and they take a couple of hours to be able to make their way to the surface. And so even though the neutrinos are going almost the speed of light, not as fast as light itself, they still get here first and give you this warning that a supernova has just gone off and it's time to go looking for it. So I like I said, I just love this era of multi-messenger astronomy, and it is literally giving astronomers a new way to another sense to study this kind of thing.
Yeah, super exciting. And there's also applications to, other things as well. When we heard about the press conference, I was speaking with some colleagues. We were trying to figure out what it was about. And we thought it was maybe going to be about the gamma ray burst. Maybe they found neutrinos from that. And there's so many different areas in which I think that having neutrino astrophysics will be like really complementary to other observations.
Yeah, that's really cool. All right, Carolyn, I choose, let's talk about this picture from JWST.
Ooh.
It's just phenomenal.
Yeah, so I stayed up all night and watched the launch, and then I got up this morning, stumbled to the computer, and there was this gorgeous picture from JWST.
Yeah.
So this is basically a protostar in the making. So it's not even a star yet. It's going to be a star someday. And it's this little object that's only about 100,000 years old, and it's hidden behind, basically you can see this vertical band right in the middle of the sort of the two butterfly wings right in the neck of it. Well, it's hidden in there, and that vertical band is about the size of our solar system. So that's the scale that we're looking at. And I mean, it's kind of cool in one way. I mean, we know that we see these protostars, we see starburst regions everywhere in our galaxy, and they're in other galaxies. But what this really said to me, and every time I see a JWST picture, is, darn, the power of infrared is really giving us a whole new look at the universe. And this is near infrared. This is coming from the near cam. So it's showing us these details that the larger clouds of gas and dust would be hiding away from us. So there's this baby protostar in the middle. Hasn't got enough mass yet to, hasn't accreted enough mass yet to basically turn on nuclear fusion at its core, which it'll do, some point in the future, and then it will be a star. But for the moment, what we're seeing is sort of the birth throes, and it's kind of a messy scene because baby, bursts of stars are kind of messy. But there's this huge nebula that's being lit up by the light from the object. And what that's doing is lighting up all of these details of how the basically the ultraviolet and the very hot radiation from this newborn thing is sculpting out the clouds on either side of it. So this sort of butterfly shape that we're seeing.
Now, do we know why, like, I mean, is it like jets are coming off of the protostar, or?
Well, I don't know exactly in this one, but yeah, a lot of young protostars do have jets coming off. I don't know if that's what's happening here. They didn't really say, but I bet you there is.
Yeah, and then and you've got the darker regions above and below. Are those
Yeah.
just a lack of material, or is that actually dust that's obscuring it? Because it really does look like a dark
Well,
nebula above and
it
below
is a dark
the
nebula.
neck.
Yeah.
And
And
so
you
I
can look at it. You
wonder,
can see stars. You can see stars. I don't, they didn't really give you that much interpretation on it, but there could be some of those stars are between us and the nebula, but that could very well be part of the cold molecular cloud where this is being born.
yeah,
But there's these jets or something is streaming out. There's the lights managing to escape on either side, say the right and the left, if that's the way we're looking at it. And then it's really revealing where the ultraviolet is sculpting the cloud.
yeah, I'd really like to understand
Yeah.
the astrophysical processes that are going on here that's creating this shape. Like it can't be a fluke that you've got these what look like fire hoses coming out of both
Oh yeah.
like
Yeah.
water
Yeah.
sprinklers, and then you've got what looks like a very dark, as you say, like a dark nebula around it as
Yeah.
it's
Yeah.
as it's only illuminating. So it's either it's only blasted out material in this area, or it's only the radiation is being concentrated, or whatever. But still, I mean, as you say, 100,000 years old. Like this isn't even a star yet. This is a
No,
protostar.
not at all. I mean, this is
Did
like
you see the
the first 5
comparison
minutes
image?
of birth here.
Yeah. Did you see the comparison image? So there was an
No,
image
no.
before, and well, we won't have it. Anyway, as usual, just a blurry mess, and then you get this
Oh,
incredible
yes, yes,
tack
you're right. I
sharp
did. Yeah, yeah,
image
yeah,
from JWST revealing all of the features that were not
yeah.
there
Well, the
in
one thing I
the
was
original.
wondering about, the one thing I was wondering about is the dark areas. This is stuff that even JWST can't see through. And so at some point, I mean, I'm sort of looking forward to the 30-day or the 60-day paper, whatever it is, to see what their interpretation is of that and whether or not
Yeah.
there is a jet. I guess you could look at it and, with something else and
Well,
see
did
about
you
that.
see the images that came out of MIRI versus the near cam images of the pillars of creation? You
Yeah,
really
yeah,
saw they were focusing on two different parts. So in the MIRI
yep.
image, you really got to see this faint nebulosity that was surrounding it when you didn't see that in the near cam image. And so it would be really fascinating to see this again if this is near cam, to see it again in MIRI, and I'll bet you it'll look dramatically different and
Well,
also interesting.
I'm looking at it now and I'm thinking it's almost 3D in a way, what we have
Mhm.
now. And so if you could mix the two of those together, how cool that would really look. But I actually, when I saw that, I thought exactly of the pillars of creation. What's this going to
Yeah.
look like in a slightly different set of wavelengths?
Yep. Yeah. I mean, like a green, horrible, eldritch horror, but
Yeah, like
the
it
way
was for
the way they
Halloween,
all
right?
do.
Yeah,
Yeah, the way they
yeah,
all
yeah,
do.
yeah.
Um, it's really exciting. All right, Leah, let's talk about the closest black hole.
Yes. So not only the closest black hole, but also a black hole in a very unique binary orbit. So basically, researchers found from data from the Gaia satellite, which looks at the motions of stars in the Milky Way, which doesn't seem like it would necessarily tell you that much, but Gaia has done just like an absolutely phenomenal job with a crazy amount of science, and so this is a really cool result where researchers found a star that is about 1,600 light years away, that's a similar mass and temperature to the sun, and it was moving in a very peculiar way that didn't indicate that it was in necessarily a stellar binary. They couldn't quite figure out what it was. They did follow-up observations at different wavelengths to see if they could figure out what the binary was. They didn't see anything, which led them to conclude that it's in fact in a binary orbit with a black hole, about 10 solar masses. And so this is would be the closest black hole that we've discovered, again, about 1,600 light years away in our own Milky Way. And what's really interesting about this is the fact that this binary exists. They're not quite sure how it would have formed. Most of the times when you see black holes in binaries, they're either very close in binaries with other neutron stars or black holes. That's how we get gravitational waves. Or they're in an X-ray binary with a star in which they're close enough to be kind of accreting the gas from the star into the black hole. But here, that's not the case. These two are just in a kind of coexisting, peaceful orbit that's far enough away that it's gravitationally bound, but not having any of these other effects. And so they're not quite sure how it formed, but it also indicates, because we found one so close, that these must be pretty common, existing in the Milky Way and beyond. So very cool observation.
And I know the search for this black hole was quite extensive. They went through hundreds of thousands of binary stars in the Gaia catalog and ruled them all out. And apparently there's like someone on the team who's like the black hole killer, who they narrow down the candidates, and they're like, okay, are these black holes? And I guess they just ruthlessly go through and go, nope, 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 nope. And one remained of this enormous survey that they went through of Gaia data to pull up this one black hole. So like 1,600 light years away. I mean, obviously that's far away, and even if it was orbiting this, if the sun was orbiting it, it wouldn't be a gigantic problem. But how close do you think the closest black hole is to us?
Well, some people claim that the mysterious kind of Planet 9 is a primordial black hole. So I don't know that I necessarily ascribe to that belief, but it could be as close as in our own Milky Way, some people say.
Close in our solar system? Yeah, but like an actual like stellar mass black hole, the kind like this.
Yeah.
I mean, are they in tens?
Do we really want to know how close it is?
I'm just wondering, right? Are they within?
Maybe we want to stay ignorant.
Yeah.
Yeah.
Well,
yeah.
well, hold on. Well, I think I can do some rough math here. Hold on. So there's stars are 5 light years apart, and there's like 10 billion stars in the Milky Way, and
100.
there's 100 million black holes in the Milky Way. It's estimated. So that's like, is that how many orders of magnitude is that? No, wait, is it? Yeah.
It's,
So like
one
maybe
order
a
of magnitude.
few
It's really probably
100
2.
light years away on average from us.
Mm-hmm.
Yeah. Anyway.
Yeah, seems reasonable. But I mean, probably there are some closer than that. We just haven't found them yet. But
Right. Yeah.
not too close.
Yeah.
You know,
Might be a lot
Look
smaller.
behind you.
Yeah, exactly. Yeah.
It's behind you, isn't it?
Yeah. But still, it's a great technique. Gaia just keeps delivering the goods. Like, how much
have
do you
such a
rely
crush
on
on
Gaia for your work?
Me?
Yeah. Do you use Gaia at all?
So I don't use Gaia, but I'm thinking about kind of getting into some more areas that would. But it's definitely very closely related to the things that I do, but I don't directly use it.
Yeah, I feel like
I appreciate it.
every possible question you might want to answer is in the Gaia data.
Definitely.
Or the cosmic microwave background radiation. It's in one or the other.
Yes.
Yeah. Very cool. Or it'll be in Vera Rubin. That's going to be great. All right. Carolyn, let's talk about finding a piece of the Challenger.
Right. So I think we probably all did see that story last week about a dive team finding this piece of the Space Shuttle Challenger on the ocean floor. And it's just off the Space Coast. They didn't exactly say exactly where they found it, probably for good reason. I found it pretty significant story because it's actually one of the larger pieces of the Challenger that they found. And I went and did a little digging around and found out that they've only really found about maybe 50% of the pieces of the shuttle that were left over. It's about somewhere between 15 and 20 feet across. And you could tell just from the image. And I think, NASA looked at this right away and said, yeah, judging by the tile patterns and all that, this had to be part of Challenger. So they did take a look at it. They confirmed the identification of it, and then they released a statement about what they were going to do next. They have not said exactly what they're going to do next. They're consulting with the families, the Challenger families, to see, I think, probably to figure out what's the most respectful thing they can do. The government actually owns it. So that means I think anybody that's going to go out and try and recover it would have to talk to the government about that. But they are going to confer with the families. I saw some speculation about, well, they could raise it up and put it with the rest of the recovered materials, which are in a silo. They could leave it in place. Somebody suggested that they put up some kind of memorial, like the Pearl Harbor Memorial in Honolulu, but out there. The thing that I found the most interesting, though, is this is the History Channel that found this, and they're looking for it. They found it because they were looking for pieces of shipwrecks in the Bermuda Triangle.
Oh, come
Now,
on.
the Bermuda Triangle is not anywhere near this, so I don't know if they were doing like a practice dive or what they were doing. They didn't say. But what I just thought was so ironic was that instead of reporting history, now they're actually making history with this discovery.
But do they report history?
Well, we could debate that, but
Yeah.
but they,
I'm not saying it's
I mean, they made a
aliens.
very nice statement about it,
It's
about how they
aliens.
really did feel very.
Yeah.
So it looks like it's pretty shallow. I mean, they're not geared up for
It does.
deepwater
Yeah.
drive or deepwater
Yeah.
dive.
Well, I think it's still on the continental shelf, but I don't know exactly. They didn't say exactly where it was.
Yeah. Yeah, I don't know. I mean, definitely talking with the families is important,
Yeah.
but I mean, having a memorial to the Challenger astronauts and actually having the piece, like if they're just sitting in a silo, I mean, I think they've learned everything they can from that on how to make
Yeah.
the space shuttle safer. I think it should be on display somewhere that we can go and see.
Well, there
it
is actually a
and-
piece of Columbia. There is actually a piece of Columbia on display at the center.
Yeah.
And I think everything that is on display is done with the tacit, or I don't know if it's tacit, but with the permission or with the knowledge of the families. They've
Yeah.
been pretty sensitive about that. So I do know there is that. There is some material that I know has been kept out for further study. What they're going to do with this, I think we just have to wait and see what NASA says.
Did they say how they found it? Like, did it show up on radar, or did they just happen to drop an anchor? And
the way they
there
made
was.
it sounded like they were out there looking at something. This was partially covered with sand and debris. I mean, it's been underwater for quite a while.
Like, if it was that shallow, and that showed up on radar or sonar or whatever, you think NASA would have picked these pieces up. I mean, they
Well,
must have searched exhaustively in the aftermath.
Well, these
Yeah.
guys are out diving. I don't know if radar would have picked it up, especially if it was covered with sand and other debris. I mean, it might have looked like a fairly smooth return, but I don't know.
Yeah.
Mhm.
How
It looked
far?
the way they make it sound was that it was just that they found it as they were diving looking for other debris from old shipwrecks.
It's about 20 feet across, so it's a pretty
Yeah,
big
about
piece.
yeah.
Yeah.
Well, I saw two different measurements, but yeah, it's about 20.
Yeah.
Yeah. I mean,
Yeah.
but that piece is remarkably intact.
I know, isn't it though? Yeah.
Yeah. Yeah. I wonder if it's like one of the larger intact pieces that they would have of the wreckage, which might make it more interesting to study.
Well,
All
I
right.
do
Well, we've
remember
reached
watching. Oh, go ahead.
Oh, I was gonna wrap everything up. So by all means,
Okay.
throw one last point in if you.
No,
want
I
to.
just remember watching the day that it happened. These large pieces falling into the ocean, and that's kind of what I thought when I saw this. Is this one of those? That was what really brought it home to all of us that this had happened.
Yeah. I try not to, if you read accounts of that day and what happened, like it's horrific. It's so
Yeah.
sad what must have happened. All right, but
Anyway, it's an interesting
we've reached
find,
the
very very
end.
historical, and there we go.
Yeah, well, we've reached the end of our hour, so I want to give my co-host a chance to talk about what they're working on. Morgan, what are you working on, and where can people find out more?
Yeah, well, as always, check out my work over at EOS Magazine. I wrote a cool piece recently about the effort to develop a forecast model for lava flows that is fast enough
Cool.
that it makes you allows you to make weather predictions for lava flows to help people evacuate safely in the face
cool.
of eruptions, it's pretty cool stuff.
That's great. Leah.
Yeah, I've been working on several different projects. I'm thinking a lot these days about gravitational waves, which is pretty exciting, especially with LIGO experiment upgrading at the moment. Yeah, and you can find me on Twitter still at Leah G. Jinx, and also my website is leahjinx.com.
Yeah, in case Twitter isn't there, even by the time you go to look her up. Carolyn.
Still digging around with planets, working on a book, and writing for Universe Today. And you can find me there. You can find me at thespacewriter.com, and I'm on Twitter for as long as it takes, and at Space Writer.
So I've got a really cool interview that I did this week with the researcher behind the tree rings and the giant solar flares, and it was fun and terrifying all together. So that was really interesting. If you want to check that out on my YouTube channel. We're coming up to our 200th questions and answers show on my channel this week, and I don't want to spoil it, but what we're working on is going to be a ton of fun. So if you want to, definitely come and check out my YouTube channel mid next week, and we will have our 200th episode, and it's going to be something special. So definitely check that out. All right. Well, thank you everyone for joining us this week here for this action-packed episode. I think this is one of the densest. I don't think I've worked so hard to moderate a show as I have, because there was just so much amazing news. What a week. But thank you to my co-hosts for joining us this week. Thank you to our special guests. Thanks to all of the moderators, everyone watching us on YouTube and on Twitch. Thanks to Nancy for organizing us all. And thanks to Pamela for engineering behind the scenes. And we will see all of you next week. Thanks, everyone.